For the past 4 months, I've been working on a project involving group theory, twisty puzzle geometries, computer algorithms, and gears. In this video, I'm excited to finally present the first physical results of the project. This is the DoDot M12. It's just like the original DoDot puzzle, but with certain sets of 3 turning axes tied together so that they move simultaneously. The axis system is chosen very carefully to enforce an unusual property that makes this puzzle unique. The positions of the dot pieces are restricted to behave according to the rules of the Mathieu M12 permutation group. This limits their possible scrambling outcomes to a small subset of the possible positions of the regular DoDot. The original puzzle permits about 200 million different positions, whereas the dots on the M12 can only reach 95,040 possible positions. If you break down these numbers, it reveals a bit about the behavior of the puzzle from a solving perspective. On the regular DoDot, if you solve each piece one at a time, the first one you pick has 12 possible places it can go. After you decide where to put it, the next piece has 11 options. Repeating that until the 10th element, it has 3 places it can go. Since the factorization ends here, solving the 10th requires the remaining 2 to automatically fall into place. So on the regular DoDot, the simplest operation, as with most Rubik's Cubes, is a 3-cycle. In contrast, the factorization of the M12 group ends at the 5th element, implying that once you've correctly positioned 4 dot pieces and go to solve the 5th, the other 7 must end up solved at the same time. This might sound like it makes the puzzle easier, but it's tricky because every possible move or algorithm affects 8 or more dot pieces, so you can't exactly break it down into small steps. The hardest part of prototyping this puzzle was perfecting the base DoDot mechanism. Since one side has to turn 2 others simultaneously, any little bit of friction really adds up. This current prototype is really loose compared to the previous iterations, but that's what it took to get it turning well. Inside the core is a gearbox with 4 layers that connect each group of axes. 3 plastic axis gears mesh with a circular gear rack such that they all move in the same direction. The gear racks were 3D printed in stainless steel by Exact Metal on their laser powder bed fusion machine. Each layer has rails holding everything loosely in place, which then get covered up by 4 spherical shells and bolted together. The gears connect to the spindles on the outer puzzle using a sliding mechanism that allows the use of standard screws and springs to tension the outer layers. In designing this puzzle, I wanted to express the M12 group in the simplest way possible without distracting from the solve with other pieces. This is why the petals are grayed out. I wanted to make the 12 dots the highlight of the solve. The edges exist in 5-piece orbits, which all behave independently from each other and are easy to solve. Once the edges are solved, it becomes clear where the dots need to be positioned. This is a really nice feature of this specific axis system. The disadvantage is that here, 8 of the axes are locked and don't move at all. There are other ways to express the M12 group on a vertex-turning dodecahedron, and the ones that maximize the number of utilized axes are highly symmetrical. Some of these representations were first discussed in 2018 on the Twisty Puzzles forum when Bram Cohen inquired about their existence. Caitlin Neely likely discovered the same axis system used on my puzzle. William Kretschmer discovered and described another particularly nice representation that involves gearing together groups of 4 axes instead of 3, and patterning them 5 times, leading to all axes being used. This representation, as well as the DoDot M12, demonstrate snub tetrahedral symmetry, having distinct chiral forms. The snub tetrahedral symmetry of the M12 led me to wonder if it's possible to represent another Mathieu group, M24, over the 24 vertex snub cube geometry. It turns out that yes, this is the case. There are M24 representations that are directly analogous to the icosahedral M12s. These constructions could be geared using a 24-sided pentagonal icosahedron puzzle that looks a lot like the DoDot. I started prototyping it, but it's turning out to be difficult due to internal jumbling. I plan to continue the project by constructing more gearing systems that demonstrate other permutation groups, including M11.